First of all, I would like to thank Andreas Podelski for the kind invitation, and especially for soliciting this tutorial and the paper that accompanies it. So it was hard work to write it in a short time due to other commitments, but in the end, I'm really very happy we wrote the paper. You will see it as soon as the proceedings will be available. This is joint work with Roberto Bagnara, my brother, and Patricia Hill. So this is the plan of the tutorial. I will start with some introduction. Then I will point out some peculiarities of the C language, and in particular the fact that its semantics is not completely defined. Then I will introduce MISRA C. I will start with some history of the MISRA project and of MISRA C itself. I will also introduce briefly the guidelines, and then I will move to explaining some connections between some obvious connection between static analysis and MISRA C. Then some discussion, and then I will conclude. So you are welcome to interrupt me, to ask questions at any time if you want. So let's start with some historical remark. So in 1994, we had the first static analysis symposium. And so this marked the time when static analysis was recognized as a mature and somehow independent research field. In the same year, MISRA published its development guidelines for vehicle-based software. So in these guidelines, two things were said in particular, among many others. First thing, that to develop vehicle-based software, one should use a subset of a standardized programming language. And the other thing was to recognize static analysis as one of the most important techniques in order to prove safety of software. So apart from this historical fact, so both things happened almost at the same time. So static analysis as an independent research field and being recognized by an inherently industrial initiative like MISRA as a key technique to reason about the correctness of programs. Apart from this, the connection between the static analysis research community and the ecosystem that revolves around MISRA C has been basically unidirectional and mediated by the tool providers. Of course, the tool providers are interested in all advances in static analysis in order to improve the usefulness of their tool. On the other hand, the static analysis research community, me included, have always had an attitude of the kind, don't know, we don't even know what it is, and we don't care. So the objective of this tutorial is to clear up some misconception about MISRA C and to properly, I hope, introduce MISRA C to the static analysis community. In the last years, I have done the reverse thing. So I've talked about static analysis, abstract interpretation to industrial venues. So this is the first time I try to do the other things. A disclaimer, so I am a member of the MISRA C working group, and I am also a member of the working group that standardizes the C language. However, here I'm talking, and in the proceedings, I'm writing in a personal capacity. So whatever I say is my opinion, the opinion of my co-authors, and does not necessarily represent what the working groups what is the official position of the working groups. On the MISRA C working group, I think 12 people. On WG14, many more people. I would say 40 people. Yeah. Okay, so C has important advantages. I mean, you know that C development started almost 50 years ago, so it was 1969 at Bell Labs. And C is still here, and it will remain here much longer than COBOL 85, I think. We had yesterday an interesting talk about the analysis of COBOL 85. So the reasons are very pragmatic. First reason that C compilers exist for almost any processor, from microscopic devices that are in hearing aid devices to supercomputers. C compiler code is very efficient, and it has no hidden costs. No hidden cost means that at least on small CPUs, a programmer can roughly predict the running time. This is no longer true for current multi-core designs where the use of tools is essential to predict execution time. C allows writing compact code, so there are many built-in operators. The language is not verbose at all. And C is defined by an ISO standard. This is another important reason. And C gives easy access to the hardware. After all, it was designed to, the first stimulus was to write the Unix operating system. And C has a long history of usage in critical systems, including safety-critical, mission-critical systems. And C is widely supported by all sorts of tools. So lots of advantages. There are disadvantages. WG14 has always been faithful to the original spirit of the language, which can be, not completely seriously described by this commandment. So trust the programmer can do anything. Make it fast, even if it is not portable or if it is dangerous. Of course, many of these things, as we will see more in detail, are bad for safety and security of the application. So one of the essential things about C is that the behavior is not completely defined. So the key concept in the standard is I'm citing the standard C99, and the version you can download for free. Otherwise, it will cost you 170 euros to get the PDF version of the C standard. Okay, so the key concept is the one of behavior, external appearance or action. So something that is visible on the outside. And another key thing is the as-if rule, which means that the compiler can do anything, any transformation that preserves the observable behavior of the program. This is true for not only for C, it is true for almost all, I would say for all compiler languages, because in order to achieve some efficiency, the compiler must do transformation. So together, these two imply the existence of non-definite behaviors. So the most dangerous category is undefined behavior. It's a behavior upon which the standard imposes no requirements. We'll see examples. If you do this thing, the program can do just anything. It may crash, it may format the hard disk. Okay, this is almost a joke, but indeed it can do this, and without violating the standard, can make the program engage erratic behavior of any kind. So here are two examples. So the program may attempt to modify a string literal. This is undefined behavior. Or the program tries to write on a string that was returned by getenv, like in the example, or str error, or other functions provided by the standard library. Another example, the value of an object is used, an object with automatic storage duration, so say a variable on the stack, to make things clearer, is used while it is undeterminate. So if you read a variable on the stack that has not been initialized, this is undefined behavior. I will not go into this, but the C standard makes room for trap representations, so there are configuration of bits in memory, such that whenever you try to read them, a trap will, okay? So this is another source of undefined behavior. Then there is another category that is unspecified behavior. This is less dangerous in a sense. So it is when there are two or more sensible possibilities, two or more sensible implementation, and the standard imposes no requirements. And the compiler needs not document what is the choice, and the compiler can make different choices at different optimization level, at different version, without letting you know. So one example is the order in which operands of an assignment operator are evaluated. Here there is an example. You don't know whether this will be evaluated first or this will be evaluated first, and the result of the program may change. Okay? And it may be the first result. Maybe you compile the same program with a different optimization, it will be the second. Maybe you have a function that to you looks completely identical, and on the first one it will do this, and the second one it will do that. Implementation defined behavior is unspecified behavior where the documentation needs to document what is the implementation choice. So this is known by almost everybody. For example, the fact that the sizes and implementation of basic data, such as int, is defined by the implementation. There are C implementation with 8-bit integers, 16, 24, 32. Okay? Another example is whether plain characters, that means the char type not preceded by the keyword signed or unsigned, is signed or unsigned. It can be both. Okay? This is another implementation defined aspect. Another implementation defined aspect is the semantics of some bitwise operation on signed integers, because signed integers in C can be implemented in a variety of ways. So it can be complement to 2, complement to 1, modulus and sign. The negative zeros might be legal values or maybe trap representation. This is decided by the implementation. And concerning, for example, the right shift, if the quantity to be shifted is signed and has a negative value, then the resulting value is implementation defined. Here an example. So we are shifting -1 to the right of 2 positions. We can get either -1 or this number or something else. Differently from unspecified behavior, reading the compiler documentation, we will know what it is. And then there is local specific behaviors, not very interesting for this talk. So it is behavior that depends on local conventions, nationality, culture, and so on. Here is a simple example. So in the Italian locale, the 15.5 will be probably written as 15,5. Okay. So why is C not fully defined? Why we have all these classes of not completely defined behavior, and there are hundreds of such non-definite behaviors. So, okay. So the reason is to make writing the compilers much easier and to allow them to generate faster code. So the reason is that whenever it is possible, a language construct will be mapped to the simplest sequence of machine instructions that realize the thing. Okay? Even for this reason, the thing is not completely defined. We'll see examples. So with undefined behavior, as we said, anything can happen. The program may fail to compile, it may crash, it may corrupt memory, it may even do what the programmer wanted just by chance. So what happens is that the compiler is free to assume that undefined behavior does not happen. Okay? If it does happen, it is a fault of the programmer, and there are no warranties about what the programmer might do. So here's an example. So an overflow on an integral type with sign is undefined behavior. So this function here can be compiled this way, because one could naively say, okay, v plus 1 will not be greater than v if v plus 1 overflows. But the point is that the compiler can assume that it will not overflow. So it is completely legal for and actually this is done by compiler we use every day. Okay, so This is an interesting example. Another example is the program attempting to modify a string literal. So suppose we have a program where there are two literals. One is tail, and the other is head-tail. It is perfectly legal for the compiler program to only memorize the first one and provide a pointer to the capital T as a representation of the second one. So if you change one, you change the other. But the compiler can assume that you will never, ever try to write to a string literal. So the compiler assumes this will never happen. Another example, you try to shift an expression by a negative number or by an amount greater than or equal to the width of a promoted expression. Okay? So one would say, okay, what could be the semantics? I'm shifting this quantity to the right by a negative quantity. So it could be a shift to the left. But this would require a test, okay, a jump. So no. It's more subtle to understand why should this be undefined behavior. I push 32 zeros to the right of a 32-bit quantity. The result should be 0. No. Why? Because architectures as popular as the IA32 applies a bit mask on the shift count in order to have the maximum execution time of the instruction bounded. Okay? Imagine what would happen if you, by mistake, you'd shift by, I don't know, 1 billion positions. So the execution time of the instruction could be very long. So what happens on this architecture? Shifting by 32, it's the same as shifting by 32, masked, keeping only the 5 bits of lower significance. So it's like shifting of 0 position, so which is a no-op. And for this reason, the C standard says it's undefined behavior. You shouldn't do it. Okay, if you do it, warranty void. Okay, MISRA C now. So MISRA is a project that started in 1990, and it came out of an initiative of the UK government's safety program, and the mission was to provide world-leading best practices for the development of safe and secure application. So it is now a self-supported project. There is a private company that provides the project management, and that's all. So the aim is to develop and promote best practices in the engineering of safety-related systems, and in particular to develop guidance in specific areas like the C language, and is what this talk is about, C++, model-based development, and so on. MISRA does not run certification schemes, so there is no MISRA certification of any kind, and does not promote or endorse specific products. So these are the first two important publications of MISRA related to the present tutorial. So this, to the left, you have the development guidelines for basic vehicle-based software of '94, and to the right, you have the first version of MISRA C, dated 1998. What is interesting about the development guidelines of MISRA is that they came more than 10 years before work started on ISO 26262, which is the current standard for the development of vehicle-based software. Okay. And then MISRA published a lot of other publications. So I don't know, MISRA C++ is something we'll see again in a minute. So MISRA C, as I said, the first version came out in 1998. The first version was obtained by combining the efforts that Ford and Land Rover were doing in-house to develop their own coding guidelines. And then a committee produced the first version. So then there has been a second version in 2004, which was based on user experiences beyond expectation. MISRA C was adopted in industry sectors, not only automotive industry sectors, but also railways, aviation, and so on. And the latest version, which is the one on which I focus, is MISRA C 2012. So it was released actually in 2013, after 4 years of work. So it supported C99. So one of the things someone might wonder about is, okay, now we have a C11, and we are close to have an even recent version of the standard. The point is that the industrial world is very conservative. So C11, it's too complex for the moment. So we'll wait another little bit, so in order to allow the compilers time to stabilize and so on. So, okay, MISRA C 2012 presents several improvements with respect to the previous version. In particular, it provided expanded rationale. So it better explained why a rule is there, which bad things it is supposed to prevent, and so on. So this a picture resuming the history of MISRA C. We have Ford and Rover developing their own coding standard, putting them together with some other work into MISRA C 1998. This influenced the development of Lockheed Joint Strike Fighter coding standard for C++. MISRA C 2004 is a direct successor of the first version. And both JSF++ and MISRA C 2004 influenced MISRA C++ 2008 that contains also an important contribution by the United Kingdom Ministry of Defense, who funded a work package to produce what is missing, what was missing in the MISRA C++ standard. So a list of all the non-definite behavior of C++, which was present in the C standard but was not present in C++. And both of these have been the basis for the development of MISRA C 2012. So, as a member of WG14, I often receive sort of complaints, I mean, of the form, you in WG14 should fix the language. It's all your fault, because undefined behavior is your fault. So what these people doesn't realize is that the weakness of the C language comes from its strength. So the fact that there are many compilers producing efficient code for almost any architecture, it is there only because there is non-definite behavior, okay? Efficient code with no hidden cost is there because there is no runtime error checking, okay? The fact that there are today in existence 1,000 different compilers and that there is an ISO standard implies also non-definite behavior. The standardization process is driven mostly by economical reason. Okay, there are technical reasons, but the economical aspect is crucial. You cannot standardize something that from today to tomorrow says that the compilers produced by these 12 companies are no longer C compliant, okay? So in many cases, having non-definite behavior is the only way forward to have a standard which everybody agrees upon. So the fact that you can easily access the hardware is of course, it's the obvious consequence. It is so easy to corrupt the program state. Okay. The fact that you can write cont'd code, this is the reason why the language can be easily misunderstood and misused. So, of course, this is not good, because we want safety and security of the application. And for this reason, language subsetting is crucial. This is mandated or recommended by all safety-related standards. So in industry in general, automotive, railways, aviation. And today, the most authoritative language subset for the C programming language is MISRA C. So now, some things are very important to understand what is MISRA C. So the first thing I wish to draw your attention upon is that the highest payoff for the adoption of MISRA C is when it is adopted from the very beginning of a project. So, and when it is systematically enforced with a tool of sufficient quality. So taking an existing project, imposing MISRA C, running the analyzer, and detecting the violation makes almost no sense, and may even be counterproductive. This can be done only in very particular cases. It requires a lot of expertise and tools of even higher quality. Okay? And the other important thing is MISRA C is part of a documented software development process. It doesn't make sense in isolation. Okay? So the process must ensure that the software requirements are complete and consistent. It must ensure that the design specification that arrive at the coding phase are correct, consistent with the requirements, and do not contain spurious stuff, that object modules produced by the compiler behave as specified in the design, that the modules have been tested both individually and together to identify and eliminate errors. And of course, due to this, MISRA C should be used before code reaches the review and unit testing phase. Otherwise, you can expect a lot of rework. You can expect having to rewrite much of the code. Okay? So the details about the software development process are outside the scope of MISRA C. But the development process are standardized in documents, in standards that apply to the individual sectors. We have seen all of those, these railways, these medical devices. So in order to use MISRA C, there are some activities that are absolutely required. So in order to use it, it is necessary to develop and document a compliance matrix showing how compliance with the MISRA C guidance is checked. And a deviation process must be put in place whereby justifiable deviation can be authorized and recorded. The software development process should also document and demonstrate that runtime errors have been avoided, for example, to make sure that the execution environment has sufficient resources, so computing power, memory, stack space, and that runtime errors, such as overflows and other things, have been excluded by virtue of static or dynamic checks. One of the common misconceptions about MISRA C is that it has to do with coding style, programming style, like the presence of spaces or uLines or the name of variables. It is completely false. Okay? So it is an activity that is recommended by MISRA C. It is known that a consistent style facilitates peer reviewing. Okay? But since style is a matter for individual organization, MISRA C stays completely away from this. It says each organization should adhere to a consistent programming style. Similarly for metrics. So it is known that software processes can be helped by metrics in order to identify code that requires special attention, but which metrics should be collected, how should be used, this goes completely beyond the scope of MISRA C. So MISRA C 2012, you can buy it for 10 times less the price of the C standard, so it's 17 euros PDF. And you will find rules presented in this way. So first thing, there is a pink strip where you can find a unique identifier for the guideline. The guideline is composed by a keyword, that can be rule or directive, followed by a dot decimal identifier. And the remaining text is called the headline of the guideline. So a directive is a guideline such that, in general, the code does not contain enough information to say if there is a violation or not. So In general, you have to take into account requirement specification and designs in order to say this code contains a violation or not. Whereas a rule is a guideline such that all the information is in the source code. Okay, so in principle, what happens is that a static analysis tool may help to check compliance with respect to a guideline if the tool is provided with the extra information required. Whereas for a rule, discounting undecidability and the availability of enough resources, a static analysis tool should be able of checking compliance with respect to the rule, providing a yes or no answer. So one thing to be understood is this, that the headline is just a short summary of the guideline. The headline is not the guideline. It is there just to have some mnemonic value, okay? If I say rule 9.1, it means nothing. I may forget in 2 minutes what it is. So if I read the headline, I will remind myself what is the rule. So in general, a description of a guideline takes pages, and all of this should be studied in order to properly understand what a rule is about. Then a rule is tagged with several fields. One is category, which may be mandatory, required, or advisory. Analysis, it's a pair of the form decidability and scope, where decidability may be decidable or undecidable, and the scope may be system or single translation unit. There is also another field called applies to, which is one or more of the keywords C99, because some rules apply only to C90, and some rules apply only to C99, because things are present or not present only on one of this version of the language. So a mandatory rule should be complied to. No deviation. So if you violate a mandatory rule, the program is not MISRA compliant. Whereas a required rule shall comply for where it does not comply, you should provide a formal deviation. And this is something that is specified clearly. So you have to write down why you deviate. You have to convince a peer that the deviation is necessary, that it is safe, and that you will do all the extra verification steps to make sure that the bad thing doesn't happen. Advisory rules are recommendations. They should be followed as much as it is practical to do so, and otherwise can be deviated. Formal deviation is not necessary, but you have to record non-compliances. You have to write down, this advisory rule is not followed here and here, okay? There is no other grading of importance between the rules. So it's not the case that rules are more important than directives. The relative importance is only in the category, mandatory, required, or advisory. So in this audience, I will skip completely the thing about decidable and undecidable. So you, of course, know what it is. And of course, MISRA C lives in a very pragmatic industrial world, whereby even if the rule is decidable, limitation of available resources might prevent the use of exact algorithms. So decidable doesn't mean that you will always have the optimal thing. Of course, decidability has deep consequences. Even here in this audience, this is just a reminder. So for undecidable rules, or for rules where you are not using an exact algorithm, you will have to do with the don't know messages in addition to the yes or no. And every tool must make a choice. So one possibility is suppress the don't know messages, so you will have possibly false negatives and no false positive. Or you can emit the don't know messages as yes messages, so you will have no false negatives, but you will have false positive. You can do a combination of the above, so you can have both false negatives and false positives, or you can emit the don't know messages as caution messages. So you have no false negatives, and you have somewhat confined the false positives. These are the so-called oranges of polyspace. Okay? Scope of the analysis. A rule is marked single translation unit if you can detect all the violation in the program by checking each translation unit in isolation. Whereas if you need to check more than one unit, 2 or more, or also the entire program, then the rule is marked as system. Okay, then there is the amplification. It's a more precise description of the rule. As I said, the headline is only a short summary. Then there is a rationale, an explanation of why the guidelines is there. Maybe there are exceptions. There are cases in which the rule does not apply. Almost always there are examples showing compliant and non-compliant code. There may be references to other rules, or guidelines in general, and references to the applicable sections of the standards, C90 or C99. Okay, so static analysis and MISRA C, the majority of the guidelines are decidable. So, and this means that can be checked with algorithms that do not need non-trivial approximation of control flow or of data flow. Still, these algorithms can be very complex. For example, pre-processing, that is an essential part of the translation of C programs into machine code, is a source of complication because some rules may depend on the code before preprocessing, after preprocessing, or on the relation between the code before and after preprocessing. So providing checkers for even decidable rules may still be challenging. So from now on, I will focus on guidelines whose check requires or significantly benefits from semantic-based analysis. Must be taken into account that, of course, any undecidable rule has a decidable approximation, and depending on the willingness of the programmers to restrict themselves to a subset of the language, this approximation might not be so bad. For example, rule 17.2 disallows recursion. A sensible, decidable approximation requires finding cycles in the call graph and flagging as potentially non-compliant all the function calls via pointers. If you don't use function calls via pointers, and this is true for the majority of code you can find in an embedded device, then you don't even have false positives. So why not using the simple algorithm? So here is you will find this in the paper. Now I cannot go through them. So these are 40 rules that can benefit significantly from semantic analysis. What you see here are not even the headlines, are rough, very rough one-line summaries. So I couldn't present the real headlines due to copyright restrictions. So these are paraphrases, very short, just to give you an idea what the guideline is about. So you see that I have 4 directives at the beginning. So directives, I remind you, require more than the code to be checked, but these directives depend on undecidable properties. So semantic analysis can significantly help checking.
What's the difference between unreachable and dead code?
So unreachable code is code that you cannot reach. A dead code is code that you can reach but does nothing. X equals X, and X is non-volatile. It does nothing. Okay? It's useless. It's you can remove it and nothing changes.
Forbids defensive code.
Yes, this is the usual. The point is that the compiler will compile out defensive code. So for defensive code, as part of the activity, I am part of the MISRA C liaison of WG14. We are proposing an extension to the C language in order to instruct the compiler, you shouldn't compile out this. No matter if you can prove that, I don't know, this, no, okay. So, but the point with defensive code is that under the as-if rule, the compiler can completely remove it. Okay, so yes, okay, this is a rule we have seen. So right-hand operands of a shift operator must be in range. We have seen this. And okay, and here we have characterized the guidelines according to to give you a grasp of the information that is required in order to check them. So, control flow information and data flow information. Of course, it is very well known that control flow influences data flow and data flow influences control flow. But here, we are talking only about the final result of the analysis. So, at the end, okay, whether you need the control flow information or data flow information or both, and data flow is subdivided into two columns, whether you need information on the value of pointer variables, or you need information, or maybe you need both, on numerical variables, including offsets to pointers. Okay, so it's not really, this makes sense only when consulted with the paper, so now I cannot say much. I will only say that I will use this, the stars means that I will talk again about rule 9.1 in a second. Okay, so you see that out of...
Somewhere marked both, right? I mean, somewhere marked both control flow and data flow.
Yes, yes, yes. So there are 173 guidelines in the current version of MISRA C. This includes the safety, security-related rules that have been added recently, and 40 of them depend on semantic properties of the program. So this means that research in semantic static analysis is very relevant to the MISRA C ecosystem, provided that a few important points are properly understood.
They are all undecidable, the 40?
Yes, yes. So, I stress it again, that MISRA C cannot be separated by the process of documented software development is part of. Okay? So, MISRA C is part of an error prevention strategy. And this has very little to do with bug finding. Bug finding is a completely different activity. Bug finding is an activity whereby you want to find some bugs of some classes, okay? Whereas in MISRA C, you want to prevent a precisely specified list of things, okay? And first thing to be understood is that the violation of a guideline is not necessarily a software error. For example, there is nothing wrong in converting an integer to a pointer, casting an integer to a pointer. And it is actually necessary when you want to access memory-mapped device registers. Okay, you have to do it. So, however, since these conversions have a number of problems, they are implementation defined, they are undefined behavior cases, there is a rule saying that you should avoid such conversion in all cases apart from the very specific cases where they are required and safe. So the deviation process is an essential part of MISRA C. And in fact, the thing to be understood is that the point of the guideline is not you should not do that. The point is, this is dangerous, you can do that, but it must be needed. It must be safe. And you must be able to convince a peer, an engineer with a comparable experience, that both 1 and 2 hold. So that it's actually needed and safe. One useful way of thinking about MISRA C is to considering as guidance to a peer review. Okay? You take the violations. The violation will point to section of code, hey, here you are doing something potentially dangerous. Do you know what you are doing? If this is intentional, we write a deviation. We are doing this for this reason, and we know we are safe for this reason. Okay? And if not, we change the code. Another thing that separates MISRA C from bug finding is the attitude with respect to false positives and false negatives. So bug finders are tolerant about false negatives, but absolutely intolerant about false positives. People who were yesterday in Tapas heard this from the very voice of people working in bug finders. People who follow the development of the Clang static analyzer will see that whenever there is a report, hey, I have a false positive, they will change the code. And without no consideration, are we introducing false negatives? How many false negatives are we introducing? They don't care. And this is not the attitude of MISRA C. MISRA C, it is true, false positives are a nuisance, a significant nuisance, but false negatives, if the tool has false negatives, it means, since in the end you have to prove compliance anyway, you have to use another tool, or do it by hand. So that's very different. Another aspect that differentiates completely MISRA C from bug finding is that MISRA C puts a lot of emphasis on reviews. You have to review the code. You have to review the code against the design documents. You have to review the design documents with respect to the requirements. And this has some counterintuitive consequences of the use of static analysis. One might think, okay, the smarter I can make my static analysis algorithms, the better. It is not necessarily true. So let's take the example of rule 9.1 that says that an automatic object should not be read before it is written, because this is undefined behavior. So for bug finding, the smarter the algorithm, the better. But if you use the same algorithm to prove compliance with respect to MISRA C, you are faithful to the letter of MISRA C, but not its spirit. So let's suppose that on a specific program, your smart algorithm, my smart algorithm, ensures that rule 9.1 is never violated. So this means that I have ruled out one source of undefined behavior. I've never reading a variable when it is initialized. However, maybe not now, maybe 1 month from now, 6 months from now, there will be humans during a peer review that will have the task of ensuring that the automatic variables have been initialized with the correct values, with the intended values, okay? And also, they may have to confirm that the outcome of the analysis tool is indeed correct. So, whereas if this takes more than 30 seconds or 1 minute per variable, this is not good, okay? It's intolerable that to convince my peer that this is initialized here, I have to spend more than 30 seconds, okay? It should be obvious that it is initialized, okay? So the truth is that a smart static analysis tool can follow initialization and uses across very complicated spaghetti code, but this doesn't help, okay? This doesn't help. So ensuring compliance with respect to rule 9.1, for ensuring this kind of compliance, it is better to use decidable approximations, such as the determinate assignment algorithm used by Java compilers, suitably generalized. Okay, now, so what can do static analysis research for MISRA C? What can do MISRA C for static analysis? It was already recognized in the paper by Couzeau and colleagues in 2007 that language subset can considerably help the development of precise and efficient static analyzer, because of course you can simplify things and your static analysis techniques need not be very precise when for features that are excluded by MISRA C. So it's not really important that you track unions so precisely or backward go-tos. It it is not, a surprise that things that are ruled out by MISRA C are also the most problematic for humans to reason about, are the most problematic for tools to reason about, okay? So, another area where there is room for collaboration between the communities is the development of annotations. I'm saying this because in the MISRA C working group, we are currently working on annotations. So, during the last 20 years, we have seen a lot of proposals for annotation languages. They are usually tied to one tool. So we have the annotation language for the Frege program verifier, program prover, sorry, a different annotation language for Escher C. We have ACSL and the executable counterpart EACSL for Frama C. VCC, very fast, all of those have different annotation languages. So, as I said, we are working on a tool-agnostic annotation language. The objective are to improve the quality, mainly the precision of static analysis by allowing the user to specify information concerning developer intent, precondition and function, and so on, to work better with adopted code, meaning library code, legacy code, code for which we don't have the source. And most importantly, we need this to be accessible to the majority of C and C++ programmers in a form that is easy to read and understand. So to make things clear, ACSL has already been discarded. It's too complex, okay? It's too complex. It requires personnel that is not readily available in industry. It requires notions of logic that are not easy to find. So we are looking for something easier. So I think I'm in time. I told you that C is the, sorry, I tell you now. C is the most used language for programming of embedded system. And it is here to stay. Until a few years ago, people were saying, it will eventually be replaced by C++. C++ is not going to happen anytime soon. And also, if you have been following the development of C++, you see that the language is growing at a pace that industry cannot tolerate. And in the March, in the meeting at Jacksonville, Florida, this year in March, the MISRA C++ committee, sorry, no, not the MISRA, the C++ standardization committee has written, black and white, that the committee will consider changes and improvements to the language even if this causes existing code to behave differently or not to compile. So, and this is, I think, this is my personal opinion, this is what will completely scare away the industry world. So the advantage of C comes with corresponding disadvantages, and so this implies that in order to develop safe and secure system, language subsetting is crucial. I hope I have explained the important ideas behind MISRA C, especially the fact that it is part of a more complex software development process, and static analysis is essential to the automatic verification of many MISRA guidelines, but some care must be exercised in order to not to fall into traps I have tried to highlight. And there are concrete possibilities of further collaboration between the static analysis community and the MISRA C ecosystem. So thank you very much for your attention. It's me before the accident. Yes.
So thank you, Roberto. Questions? Doesn't work, so.
For the production, For the production of embedded critical software, C is often used also as an intermediate language by tools like Simulink, SCADE, and
Yes.
do you know if these tools produce C code that comply that are far from complying to
Okay. So two things. One thing is that MISRA has special provision for auto-generated code. So there is a section of the document that explains what to do with auto-generated code. And I think the rest of the question is that there are some code generators that claim MISRA C compliance, and the question is, are they actually compliant? Not in general. Not in general. I mean, we see this in the work at Bugsang. No. But I mean, the fact of using a code generator does not exempt you to have a tool to check things. So, okay. So, I mean, you can write a deviation. So what can be done? What is usually done? You write to the provider of the code generator. You say, okay, even in MISRA compliant mode, a non-conformant code is generated, so please fix it. And meanwhile, you examine whether the violation is dangerous or not, and you write a deviation if it is required rule. If a mandatory rule is violated, you are in trouble because you cannot claim compliance, MISRA compliance. Yeah.
Patrick?
When you say semantic static analysis tool,
Si, yes.
there are some strange ones like coverity, which are neither sound nor complete nor anything. And when they say something, you never know anything. So is it in your list of static analysis tool? Or
Well, yes, it is in the list of tools that do some reasoning on the semantics, and they probably are in the class of those that have both false negatives and false positive, and yes, so you cannot really rely on the results. The best you can do is to examine the messages and check them yourself. Whether
okay. So you cannot conclude anything, you have to do it by hand.
Yes, yes.
So
you can use such tools as hinters. I mean,
So it's a noise.
I mean, using a bug finder to do MISRA C compliance is completely useless. You must have some sort of guarantee. So yeah.
Other questions? Andreas?
Yeah, so it was on your conclusion slide, you talked about verifying the validity that these guidelines, the validity of the guidelines, yeah, so automatic verification of guidelines. So these are verification problems. Can you say what is specific about these verification problems? Is there anything
Nothing.
specific?
Nothing.
And
Nothing. I mean, many of these rules are based on verifications that are done. I don't know. So, I mean, the absence of buffer overflows is there. Okay. The fact that you do not dereference null pointers is there. It is done by several tools. It's done by, I don't know, Infer, Astray. So it is not an either or. I mean, I'm not talking. So MISRA C is based on program properties that have been studied over the last 50 years, I would say, yeah, 40 years.
And you said that afterwards there is a manual verification that the guidelines are valid. You said that 6 months later people come, and so I didn't quite understand. So do you do automatic and manual verification?
So the point is this: in the processes, in the standardized processes used to develop critical code, you trust nothing. Okay, so either you check the result of a tool, or you do some activity to prove that the tool is correct. Prove in maybe testing, okay? So you have to gain confidence in a tool. So it is not an unusual activity that you really have to study a violation or the absence of a violation to understand whether the tool is correct or not. The fact that the tool vendor declares there are no false negatives may not be enough. I mean, tools have bugs. Okay.
And so maybe so my favorite property is termination. Is it part of a guideline? Loops must terminate?
Yes, it's not, I mean, this is a very semantic guidelines. This rule is not there. So it specifies a restricted forms of for loops that you have. I mean, you can write a while loop that doesn't terminate, okay? But there are a set of rules that are meant to restrict the use of for as if it was a for in Pascal. So the terminate iteration.
But you do have while loops.
Do have while loops, yes, because there are embedded systems that legitimately do not terminate.
So there is a guideline about termination?
No, there is a guideline about restricted use of for loops.
Maybe a last question by Thomas.
So on your slide that you have safety and security, but I have the impression that the automotive industry is mainly, so far, has been interested in safety. So have you had any guidelines sort of more dedicated to security properties, like
Yes.
in isolation and
Yes.
integrity?
So in 2016, the MISRA C working group has published the Amendment 1 to MISRA C 2012 that contains 14 new guidelines that have been added to MISRA C. Now here I have considered the complete thing. So when I say 173, this comprises the 14 rules. And with these rules, MISRA C 2012 covers the ISO technical specification, I don't remember the number, 18, it's called, the nickname is C Secure. So it's a technical specification by WG14 concerning the use of C for security, okay? So it's a set of guidelines, okay, in itself, and MISRA C with Amendment 1 covers completely this C Secure standard. Okay. Oh, another thing, so when you have a MISRA compliant code, doesn't mean that your code is correct, and it doesn't mean it is secure. It means that it is as safe and as secure as if it was written in Pascal. We stop here, okay? So we stop here. Can be compliant and compute completely, no? Can give away your password, no, to the world. So there is a guideline about not trusting any external source, but there is no guideline saying you shouldn't publish your credit card PIN on the web. So.
Okay, so let's thank again Roberto for this interesting tutorial. And so